Hello everyone. So today we're going to continue on 7.4. So the last one we talked about in last video was a definition on how to transform a xy coordinate system double Riemann integral into a polar coordinate r theta double Riemann integral. So the formula is right here. So we're basically changing the function f of xy into f of t of r theta. So forming this composition will allow us to actually use r theta as the new variable. And we also have to change our regions B, which is in the xy coordinates, into a corresponding regions D in r theta coordinates. And of course, the last thing we have to do is change the dx dy into dr d theta. And I mentioned to you that you have to put in this r to correctly scale dr d theta as dx dy. But last video, I didn't get to explain why that is the case. As a matter of fact, that is something that students often get confused because they don't understand why the r is there. And we will explain where the r came from toward the end when we talk about toward the end of section 7.4 when we talk about Jacobian theorem. But for now, it's important to simply understand that it cannot just be dx dy simply change to dr d theta. There has to be something that corresponds to this change. Now, why is that? We'll show you a simple example, a picture to illustrate that. So imagine that you're in the xy coordinate system. And let's say you pick a point, x sub 0, y sub 0. Okay? So that point will be the intersection between a straight line and a horizontal line. And now let's say I change the x and the y coordinates slightly. Like this. And so now this is my dy, this is my dx. And so this little rectangle will be what we call the coordinate rectangle. And this is basically what the dA is, which in this case, dA is just dx dy. Okay, that is in the xy coordinate system. Okay, so that makes sense. That's where dA come from, is basically a change in area. So it will be starting this point. If I change slightly in the x and the y direction, I'm basically changing the area by this much. Now, however, here's the interesting thing. What if now I look at something in the r theta coordinate system? Okay, so same exact concept. Let's say I have this r equal to r sub 0. And let's say have this, which is theta equal to theta sub 0. And then define this one point right here, which is r sub 0, theta sub 0. If I change r and theta slightly, same thing happens. So here's my dr, here's my d theta. It would kind of form this nice coordinate rectangle. And therefore, I can say that dA will equal dr times d theta. So what's the problem? The problem is the following. If I now take this same exact picture, but... oh, sorry. Now, if I change this picture, under the transformation, now what would happen? Well, this is what happened. So here's my x, y coordinate plane. And now, take a minute to think. R equal to r sub 0 actually will form into a circle. So I'm going to draw the entire circle, but it will be something like this. And then theta equal to theta sub 0 would be a radii. That would be like this. And now if I change r a little bit and theta a little bit, what happens is when I change r a little bit, it will actually form a concentric circle and another radii. Oops. Another radius. So this is my d theta and this is my dr. And therefore form this picture right here. So this is the point r sub 0, theta sub 0, which can correspond to x sub 0, y sub 0. But notice that dr d theta would take on a completely different shape compared to dx dy. And that becomes the problem. Because if I multiply dr and d theta together, what they look like in the xy plane, it doesn't form dx dy directly. It actually form this weird looking shape. The best way I can describe this shape is that imagine you get one of those like pineapple slices where with the core taken out and then you cut a little piece. That would be how it's supposed to look like. And the problem is that this would have a different area than dx dy. And that is what the issue is. So what we eventually will find out, not right now, but I'm telling you what is going to happen, is that there is a relationship between dx dy and dr d theta on the xy plane together. There's a relationship between the two areas. And that relationship is this. If you take dx dy, which is this rectangle right here, divided by dr d theta, which is like basically this pineapple piece shape, it actually comes out to be equal to r. And that relationship turned into this one. Now, once again, where did the r come from? I cannot tell you that right now because we will talk about that in Jacobian theorem later on towards 7.4. But suffice to say that just by looking at the picture, you understand that dx dy cannot be the same as dr d theta because they take on a completely different shape on the xy plane. And therefore, they will certainly have a different area. And the ratio between the area is actually to be the ratio would actually form the r value. That's the reason why dx dy actually will equal to r dr d theta. They cannot just equal to dr d theta because that would imply that they have the same exact shape, which they don't, not in the xy plane together. See, dr d theta in the r theta plane does look exactly the same as dx dy in the xy plane. But in the xy plane, dr d theta will look very different than dx dy. That corresponds to the reason why there's a change. Now, as I say, I promise you, when we get to talk about Jacobian theorem, you understand where this r came from. Okay, so you're going to have to wait until that, and for now, just trust me on this. So what I want to do is show you how to use this change of variable formula. This formula right here that we state. So first example will be a very straightforward one. How about we just do this? We're going to use the polar coordinate system to find the area of a quarter circle and technically any quarter circle would do, but I'm going to just say in quadrant 1 just to make the quarter circle easier to do, with a radius I don't know, capital R. You know what? Let's make a numbers. Why not? Let's say 2. How's that? Okay. Now, before we move on, you should already know what the answer is supposed to come out to be, and I'm not going to tell you what the answer is because you should know, because we know how to find the area of a circle. You already have a formula for that, and you know the radius. And you know what a quarter of a circle means. So in your mind, you should have an answer already. And now we're going to try to use an integral and to see if we can get the same answer. Okay? So, show you how this works. Ready? So first of all, let's kind of draw what it is and also show what the integral would look like. So here's what a quarter circle will look like. Because the quarter circle radius 2, this point is going to be 2, 0. This point is going to be 0, 2. And the equation is probably going to be x squared plus y squared equal to 4. Okay? And the area would actually be given by this integral. And we're going to call this b. So remember, that gives us the area of b. And in this case, b is this quarter circle. What I want to do is to show you what this integral will look like in a regular xy coordinate system, and then show you how it will look like in the polar coordinate system, and then you can see the difference between the two. So to form it in the xy coordinate system, I do need to pick an order of integration. So for simplicity reason, I'm going to just solve for y and just use dy dx. So that would be what y, the equation of this top curve would be, which is y equal to 4 minus radical x. It could be minus radical 4 minus x squared, but that would be the quarter circle on the bottom. So I don't need that. I want the top one. So therefore, this integral actually going to be this. Double Riemann integral. Dy dx, there's no integrand. Our limit will be y from 0, which is the x-axis, to y equal to radical 4 minus x squared. X will go from 0 to 2. So that would be our iterated integral in the xy coordinate system. So this is our iterated integral. In xy coordinate system. Some of you might be thinking, can I just do a single integral to find this area? Seems like I can just do a single integral. Yes, you can. As a matter of fact, the single integral would be this one. Which is technically speaking what we get when I integrate this iterated integral once. Now, the problem with this integral right here, radical 4 minus x squared dx from 0 to 2, that integral actually cannot be done. I mean, well, yes, it can be done. You just have to do some trick substitution to get it to work. Okay, so that's actually an extremely difficult integral to actually do by hand. You could definitely type into a calculator to find the answer, of course, but you can't really find it like basically without a calculating device, unless you're really good at trick substitution and stuff. Lucky for us, we know polar coordinates. So what I'm going to try to do is to rewrite this using polar coordinates. So how do I do that? The first thing I need to do is to first find the corresponding regions in the r theta plane. That will give us this quarter circle. Okay, because in order for me to properly rewrite it, I do need to define a region that corresponding to the xy coordinate regions, but in r theta. Okay, so I'm going to have to do that. 2, I have to set up the integrand, but there's no integrand to set up because there's nothing in the integrand. So that's great. I do need to get rid of the differential. So in this case, with dy dx, so to get rid of them, it will become r, either dr d theta or d theta dr. So I'm going to go ahead and just put dr d theta, and I'm going to go ahead and do this first. Okay, so that way I just have a Riemann integral, and then I can set up as an iterated integral. So what I need to do is figure out what D should look like. So D has to be regions on the r theta plane that basically describe the same exact semicircle, but just in polar coordinates. So let's tell me the thing. So in order to describe it in a polar coordinate, what I need to do is describe the radius and the angle theta. So in here, because a quarter circle, it would actually rotate from 0 to the y-axis, which means this would go rotate from 0 degree to pi over 2. So therefore, I'm going to say pi over 2 right here. And then the radius would have to travel from 0 radius all the way to 2 radius. So that means this is r equal to 2. Here is my regions D. That would describe this quarter circle. Interesting thing to note, this regions in r theta is actually rectangular. Remember, one of the main reasons why we do change a variable is so that we can turn something that's non-rectangular into a rectangular region, which is what we have now. So that's the whole point of it. So now I'll show you how much easier this integral is going to be. So therefore, this is the same exact Riemann integral that would give us the area of this quarter circle. But now it's in polar coordinates. So now I can define this. So now since both r and theta are just constant in a coordinate, in a rectangle, I'm just going to pick the order that I like. I'm going to just go theta equal to 0 to pi over 2. And then r go from 0 to 2. And I'm going to say dr d theta. And I know some of you are probably thinking like, wait, but r can't be 0 in the polar coordinate. Is this going to be okay? We're going to just leave it at that. Instead, we're not going to talk about it as an improper integral yet, but we're just going to assume that this would give me the same exact result, even though r does not define in the polar coordinates. So what happened when I integrate it? So let's see. If I integrate the first time, I get 0, theta from 0 to pi over 2. Integral r dr is 1/2 r squared. You vary from r equal to 0 to r equal to 4 d theta. So plug in 0, you get 0. Plug in 2, I'm sorry. Plug in 2, you get 2 squared over 2, which is 2. So therefore become integral theta from 0 to pi over 2 d theta. That means 2 theta, you value from theta equal to 0 to theta equal pi over 2. So once again, when I plug in 0, you get 0. When I plug in pi over 2 times 2, we get pi. And I'm hoping that is the same exact answer that you're thinking using the circle area formula. Notice that this integral in polar coordinate is extremely easy to do, especially with all the limits being constant. It makes it very easy for you to plug in. Okay, so that is, this example kind of perfectly illustrate why we use change of variable. Because after we use the change of variable into polar coordinate system, this quarter circle would result in an extremely difficult integration with 4 minus x squared under the radical, which is something extremely difficult to integrate, into something extremely easy to do, which is basically the purpose of this change of variable technique. Now, of course, this doesn't seem too exciting, so let's try another one. So let's try one that, once again, that should be familiar to all of us. Let's say given the function f of xy equal to x squared plus y squared, which is equal to z. Let B be the regions bounded by, how about x squared plus y squared is less than or equal to 4? And y is greater than or equal to 0. I'm going to ask you to find the volume between z equal to f of xy and the xy planes over the regions B. All right. So let's try to understand what we're looking for. So here's the function x squared plus y squared equal to z. It's the same exact function that we have seen quite a few times since chapter 5. So here's x, here's y, here's z. So f of xy equal f of xy equal x squared plus y squared is basically this paraboloid. That's completely circular, but is basically is a parabola spinning around the z-axis. Now, what does the regions B look like? Okay, so this is z equal to x squared plus y squared. So regions B will be on the xy plane, so I'm going to draw the xy plane. X squared plus y squared less than or equal to 4 will actually form an entire circle with radius 2. But since y has to be greater than 0, imply that we basically have this part being b. So remember, this is called a boundary. X squared plus y squared equal to 4. And then y equal to 0 is right here. And so have to be greater than y equal to 0, but less than x squared plus y squared equal to 4. So therefore, this will be b right here. So top half of the semicircle. So we're basically trying to integrate this. So show you how this integral look like. So this would be, to find this volume would equal to a double Riemann integral over b, x squared plus y squared, dA. So that's what our Riemann integral look like. We can definitely set up a iterated integral in xy, and I'm actually going to do that just to show you what it looked like. The problem here is, once again, you run into this integral right here, which might be an issue. Okay, so this iterated this Riemann integral, we're actually trying to this iterated integral. So x from -2 to 2, y go from 0 to radical 4 minus x squared, and then we have x squared plus y squared dy dx. So that's my integral in the xy coordinate system. Once again, you go right into this integral of 4 minus x squared that you probably not going to be able to deal with. Okay? What would happen if I do it in the polar coordinates? Well, it's actually become a lot easier. The reason why? Because once again, what is the corresponding regions in r theta that would describe this semicircle? Well, we did a quarter circle, which is this. Semicircle would just mean that we rotate more than just pi over 2. So therefore, in this case, we're actually going to come out to be something like this. Here's theta equal to pi. 0 to pi is a semicircle. R will go from 0 to 2. Here's the corresponding regions D. So what would happen to this integral? So now this integral have more things going on. So let's try to go through this. So first of all, this would actually equal to, V would actually equal to a double Riemann integral over D, x squared plus y squared, but I do need to replace x and y with r theta. So therefore, this becomes r cosine theta square plus r sine theta square, dA, which become r dr d theta. And I'm going to leave a parenthesis right here, otherwise it's going to be confusing. Okay, there you go. Now, hopefully someone recognized what happened with r cosine theta square plus r sine theta square. This would become r squared cosine square theta, oops, plus r squared sine square theta, where you can actually factor out the r square and give you cosine square theta plus sine square theta, which that just turned into 1. So therefore, my volume actually equal to integral theta go from 0 to pi, r go from 0 to 2, integrand become r squared times r, which is r to the third dr d theta. So that's a lot easier to integrate than the radical 4 minus x squared. Okay, so now I can go through the integration. So v would equal to integral from theta from 0 to pi. Integral r to the third is 1/4 r to the fourth, from r equal to 0 to r equal to 2 d theta. So putting 0 would go away, but putting 2 into 1/4 r squared would actually turn into 2 to the 4th, which is 4 squared. So 4 squared times 1/4 is 4. So therefore v equal to integral from 0 to pi 4 d theta. That just means 4 theta from 0 to pi. So I believe my answer is 4 pi. There you go. So this substitution make your integral a lot easier to deal with because now you have all constant. You also kind of simplify the integral into something nice and easy compared to this 4 minus x squared. That's going to mess you up. All right, right now it's 25 minutes. I think I will, you know what? Actually, let's just do one more thing and then we'll stop. What I'm going to do is this. So the next thing we're going to talk about is what if we want to use a circular coordinate system, but it's in R3? Well, if it's circular in R3, we actually have two choices. We could do spherical coordinate system, or we can do cylindrical. So we're going to talk about spherical coordinate system first. Okay, so quick refresh. What is the cylindrical spherical coordinate system? So that would be a coordinate transformation that went from R3 to R3. I'm sorry, U3 to R3. So a subdomain of R3. And the three coordinates are phi and theta. And that's equal to R sine phi cosine theta. R sine phi sine theta. And R cosine phi. And that's equal to x, y, z. Okay, so show you what the integral look like. So here's a definition for change of variable between rectangular coordinate system and spherical coordinate system. Okay, so kind of word the same way. I'm going to try to word it the same way as the polar. So let me just take a quick look so that I remember what. Okay, let B be. Okay, so it's okay. That's pretty straightforward. I'm going to just do the same thing. So here we go. We're going to say let B be a region in R3 with the x, y, z coordinate system. We're going to let T of R phi theta equal to x, y, z be the spherical coordinate transformation. Okay, and I'm not going to rewrite that. I just wrote that up there, so I'm not going to rewrite. And of course, we're going to define a corresponding regions to B. So let D be a region in R3 with the spherical coordinate system. So that means D is actually in R phi theta. Such that we know this is true. Such that we know that T of D is equal to B. So once again, what does that imply is the following. That's a D. What does that imply is the following. If I have the R phi theta, and then I define some kind of regions in here, which is called D. If I take this entire region and plug it into the transformation T, which is defined right here, it would turn into an x, y, z coordinate system regions. That's called B. So that's the correspondence between these two. And so now the last thing I'm going to say is what happened to the integral. So let's start with this. So let's say we have a triple integral over B, f of x, y, z, d dx, dy, dz. So remember, that doesn't mean that you have to go in this order. So, but just collectively, these are basically called dv. But I guess we can say that this is dv in the x, y, z coordinates. Okay? And that is actually can be transformed into a similar integral, but in the spherical coordinate system by integrating over d instead of b, because d is in xyz, but b is in xyz, but d is in r phi theta. And we're going to perform a composition just like in the polar case. And here's the important part. I will need to use dr, d phi, d theta, but once again, not in this order. But if you recall what we said, you should realize that dr, d phi, d theta, and dx, dy, dz both represent kind of dv, but after transformation, they got to change somewhat, and therefore the volume is probably not going to be exactly the same. So how do I correspond the two volume together? Remember, we talk about it with the polar. This picture right here, where if you have dr, d phi, d theta, which will probably form a cube just like dx, dy, dz, but once you put it through the transformation, it's not going to look the same. Because it's a curvilinear coordinate system. All this straight line could turn into curves. And therefore, you will no longer have a coordinate rectangle. So what is the corresponding between these two differential? It's actually this. So note, dx, dy, dz is actually equal to r squared sine phi dr, d phi, d theta. And of course, once again, the question is, where does this thing come from? And once again, I'm going to have to tell you that it's come from Jacobian theorems, which we'll talk about toward the end of 7.4. Alright, unfortunately my time right now, so next video we're going to start with doing some kind of example with spherical coordinate system before we move on to cylindrical, and then we're going to talk about Jacobian theorem. Alright, that will be it for today, and I'll talk to you guys again soon, okay? Bye-bye.